You built a 6-axis robot arm from scratch. You integrated OpenCV for object detection and wired it to the ROS2 framework with Movie 2 for motion planning. You expected a working autonomous system, but the reality is far more complex. The gap between a working simulation and a reliable industrial machine is not a small hurdle. It is a chasm that swallows most hobbyist projects before they ever touch a production line. By the end of this explanation, you will understand exactly why your calibration fails after 10 minutes and what architectural trade-offs are required to fix it. The first thing you need to confront is the illusion of the off-the-shelf stack. You likely followed tutorials that showcased the Francopanda or a UR3 arm running perfectly in Gazebo. Those simulations are clean. They assume rigid bodies, perfect sensors, and infinite compute power. They do not model the thermal expansion of a printed PLA part. They do not simulate the backlash in a 3D printed cycloidal gearbox. When you take that same software stack and apply it to a mechanism you built yourself, the physics engine in your head breaks down. The software assumes the arm is a solid block of metal. Your arm is a chain of printed links that flex, vibrate, and change shape as they heat up. This leads to the critical failure mode known as the last 20% problem. In engineering, the first 80% of the work gets you to a working prototype. The final 20% is where you achieve reliability, and it is where most DIY robotics projects die. The tutorials you watched skip this entirely. They show you how to get the robot to pick up a block once. They do not show you what happens when the robot runs for an hour. The cumulative error in your mechanical tolerances creates a drift that standard perception algorithms cannot correct. Consider the kinematic chain. In a simulation, the arm knows exactly where its end effector is at all times. In the real world, a 3D printed joint has microscopic gaps. These gaps create backlash. When the robot reverses direction, the gears spin freely for a fraction of a second before engaging. This creates a position error that the controller does not see. Furthermore, the motors generate heat. As the printed plastic warms up, it expands. A change in temperature of just a few degrees can shift the end effector by several millimeters. This is not a software bug. It is a physical phenomenon that the standard Movie 2 planners are not designed to handle. They assume the geometry is static. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. This mechanical variance renders your hand-eye calibration matrix invalid. You spend hours calibrating your camera to the robot base. You run the calibration routine, and it looks perfect. You start the autonomous cycle. After 10 minutes of continuous operation, the thermal drift and mechanical flex have shifted the physical relationship between the camera and the robot arm. The software thinks the object is in one place. The robot reaches for another. The result is a missed grasp or, worse, a catastrophic collision. The solution is not to tune your OpenCV hyperparameters further. You are looking at the wrong variable. The core issue is the lack of sensor noise modeling in your perception pipeline. Standard depth cameras are designed for consumer applications, not industrial robotics. They suffer from quantization errors, lens distortion, and lighting sensitivity. In a controlled simulation, the lighting is perfect. In your workshop, the lighting changes. The printed parts are often matte or glossy, causing specular reflections that confuse the depth sensor. The algorithm sees noise as an object or misses the object entirely because of a shadow. This brings us to the Sim2 real gap. You can tune a neural network to detect a block in a simulation with near-perfect accuracy, but that network has never seen the specific texture of your printed PLA. It has never seen the specific shadow cast by your light fixture. Domain randomization is the key here. You must train your vision system on thousands of variations of lighting, texture, and background noise. If you only train on clean, idealized data, your system will fail the moment the real world introduces a single variable you did not account for. There is a deeper architectural flaw in how most hobbyists structure these systems. They run the vision inference and the motion control loop on the same device. The computer has to process the camera feed, run the neural network, and then send commands to the robot. This creates latency. The robot moves, the camera captures a new frame, the computer processes it, and the robot adjusts. By the time the adjustment happens, the robot has already moved. This jitter accumulates. At high speeds, the lag between perception and action becomes the dominant factor in failure. The only way to bridge this gap is to decouple the systems. You need a modular architecture where the vision system runs on a separate edge device. This device must be dedicated to inference and must communicate with the robot controller using strict, time-synchronized ROS2 timestamps. You must treat the robot as a blind actuator that receives commands based on the most recent timestamp data from the vision system. This trade-off adds complexity. It requires more hardware and more careful network configuration. But it is the only way to stabilize the control loop against inference latency. Even with perfect synchronization and a robust vision system, the mechanical limitations of 3D printed arms impose a hard ceiling on performance. You cannot achieve industrial-grade reliability with a mechanism that relies on printed gears and flexible links. The industry standard for pick-and-place is to accept that single-shot calibration is insufficient. You must adopt a pattern where the system recalibrates at every cycle or operates with a human in the loop verification step. This is not a limitation of the software. It is a fundamental constraint of the hardware. The career gap in this field is not knowing how to write the code. It is understanding the physics of the machine you are controlling. Engineers who only focus on tuning detection models miss the fundamental need for domain randomization and the physical reality of their build. If you want to build a system that works, you must stop treating the robot as a perfect machine and start designing for the imperfections of your specific build. You must choose between a simplified kinematic chain that is easier to model or rigid industrial actuators that can handle the load. There is no middle ground. The difference between a toy and a tool is not the code, it is the architecture. It is the willingness to accept that your printed arm will drift, that your sensors will be noisy, and that your simulation is a lie. The last 20% is where you earn your place as an engineer. It is where you stop chasing tutorials and start solving real problems. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.